Hey everybody, Dave Lindberg with a new episode of THD Podcast. Today we're going to be talking with Steve Temme. He's the founder of Listen Inc. It's been one of the world's leading test and measurement companies for some time, based out of Boston. We're going to find out a bit about him, where he came from. He worked at B&K, he worked at Apogee Acoustics before, and he wants to talk to us today about correlating manufacturing defects to perception. So kind of like in a visual world, you'd say, is that a blemish on the product? So we're going to say, is that really an error acoustically in the product from what you're measuring to what people are actually hearing? So, but without delay, let's not forget to thank our sponsor, the ALTI Association. They're going to be hosting some stuff at CES, so be sure to check them out. ALTI is a great networking forum for people working in the audio manufacturing industry, so we encourage people to go check them out. All right, without delay, we've got Simon in Japan. Morning, Simon.
Evening.
And we
Morning
got
and evening.
Steve Temme in Boston area. So thanks for joining us today, Steve. How's it going?
Pretty good.
Pretty good. All right. So yeah, you started Listen back in '95 in SoundCheck, and it was a software product, and it was the first audio measurement system based on a sound card. So can you tell us a little bit about what predicated that initiative and where the idea came from?
Sure. First, I just want to thank Dave, you and Simon for having me on your podcast. But yeah, I'd love to tell you a little bit about the history of Listen and SoundCheck. So I worked for Denmark, for Bro & Care in Denmark for many years, traveling around the world to demonstrate their industry standard 2012 audio analyzer. Actually, you can't really see it, but there's one standing back here that's vintage, which I haven't turned on probably in 5 years now. But engineers liked it because it was so powerful, but they really also wanted something to use on the production line. And I had an interesting visit in Japan where they actually wanted to synchronize 6 of them to measure 6 off-axis measurements on a loudspeaker at a time. And of course, the B&K engineers were like, what? That's crazy. So in any case, it was just too slow and too expensive for a lot of applications, especially QC. And Windows 95 had just been released. And Pro Audio sound cards were also on the scene and becoming very good, very high quality, and very cost effective. So naturally, I tried to convince B&K to develop a lower cost alternative for the production test market, but they were not interested. So I ended up quitting my job at B&K, moved back to the States, and started my own company. And I developed SoundCheck based on just LabVIEW, which was already well known for coining the term virtual instruments. Mm-hmm. And I really wanted to recreate the 2012 audio analyzer and some of the other B&K analyzers and software, but I wanted to make it faster, less expensive, and more flexible.
Okay. And always the key thing with any startup business is getting that first customer over the line. Do you remember who that was?
Absolutely. And they're still a customer. So the company name is Sonotronics in New Jersey. They made military headsets, and they actually hired me to write B&K 2012, what were called auto sequences, to test their military headsets to mil standards. Ironically, the first day I met the owner of the company, he asked me if I could have done this with a PC and a sound card. And of course, I said, yeah, it's funny, I've been thinking about doing that. And he said, well, if you can come up with one of these systems at a lower cost, I will be happy to buy 11 of them. So it was actually a great challenge. And I taught myself LabVIEW and prototyped a headset test system in 6 months. So it was really quite a testimony to LabVIEW because I was not a programmer by training.
Okay. Yeah, it's always nice to get that first one over the line, especially as a startup. You've got maybe family that's depending on you, and Maybe some blood money that's financing you in the
Oh,
near
I
term.
was burning through credit cards left and right, frankly.
Yeah.
So
All
thankfully,
right.
it was 0% interest at those days for 6 months. So
Okay.
I skimped by.
So yeah, you must have seen a bunch of changes over these past like 30 plus years. You tell us some of the big significant changes that's gone through and how it's affected product development.
Absolutely. I mean, in the early days, it was all about replacing trained human listeners on the production line. And of course, QC operators at those time, it was a difficult job. It was basically listening to loudspeakers every 2 seconds with a high-level sine sweep.
Mhm.
Um, Over time, it probably damaged their hearing. And of course, they're human. They weren't completely repeatable or consistent from day to day, the usual Monday, Friday syndrome. And of course, there was no way to easily store results and statistics. So we had to prove that our test system could not only judge the sound quality like a trained human listener, but of course, catch faults and
Mhm.
save those results with background noise not affecting the measurements in a noisy factory.
Yeah, if anybody watching has been to some of these audio factories, depending on the product they're testing, they'll have a little booth with normally girls on rotation every couple hours going in and running these sweeps, but they'll still have the sweeps, but they actually have a test system nowadays. So, how has that evolved?
Yeah, it's pretty interesting because obviously those big test chambers are expensive and they want to get away from them. So in the beginning, after we rejected a loudspeaker, someone more often than not would listen to it to make sure it was correct. But we basically knew to be truly successful that we needed to create perceptual algorithms that could catch rub and buzz, what we call loose particle detection, just like a human listener.
Okay. So back then, was it just used for production or people doing development with SoundCheck as well?
Well, ironically, the same engineers that I visited with the 2012 audio analyzer and said, this is great, but what do you have for production? Now they were saying to me, this is great for production, but what do you have for R&D? They liked the cost effectiveness of it, the fact that it was fast and flexible, but of course they wanted what I would call more bells and whistles. They wanted additional functionality that you wouldn't need in production, things like time frequency analysis and intermodulation distortion. So it basically convinced me to develop a modular concept and somewhat in relation to the 2012 audio analyzer was a simple sequence editor that would make it easy to configure the system for different applications. So not just military headsets, but loudspeakers, microphones, and could also measure a lot of the same parameters using the same filtering techniques.
Okay, and that was all predicated because these sound cards and processors and computers were fast enough at that time.
Yeah, in fact, it was pretty interesting that we originally would just measure the sine sweep in one go and then analyze it, where a lot of test systems would actually measure one frequency at a time and measure the level. And it turned out that the total test time was really predicated by the actual acquisition time. So if it took 2 seconds to actually sweep and measure, the analysis time took almost nothing. So that was really because computers were becoming faster and faster.
Yeah, and huge in production when people start pumping out millions of units. Okay.
Yeah.
That was back then. So what have you seen going forward? What's kind of innovation in what you've been testing?
Yeah, so back in the early 2000s, there was an explosion of new applications, I'll say, particularly because microphones and speakers were getting less expensive. Certainly, smartphones, cell phones was a big part of it. So things like MEMS microphones were starting to get into products, as well as, headphones, VoIP phones. MP3 players was really becoming the rage. And then eventually, smartphones, tablets, sound bars, and then finally smart speakers. Just were using more and more microphones and speakers, and needed to be tested because frankly, in the beginning, the quality, of the original cell phone was pretty horrible. And nowadays, it's amazing how far it's come. One of the things that I really wanted to focus on was, how are we going to test these devices that we couldn't actually play a signal in simultaneously and measure the response at the same time? If you look at an MP3 player back then, there is no input. It was basically playing MP3 files that you loaded onto the player. So we had to figure out a way to get the test signal onto the MP3 player, hit start on the MP3 player, and then do a triggered recording and analyze the result. So this kind of coined the phrase open loop testing as opposed to closed loop, where it was simultaneous. And one of the things that we did, maybe partly accidentally, but partly by design, was we tried to separate the stimulus, the acquisition, and analysis from each other as steps. And this turned out to be very advantageous because now we could literally create any stimulus as a WAV file and load it on a device, play it back, capture it, and then analyze it. And not just for MP3 players, but we could literally go into an anechoic chamber and record our stimulus on the device under test and go back to our office, have a cup of coffee, and analyze in our office, because we could also listen to the raw recording, whether it was sine sweep or music or whatever, multitone, but we weren't under the gun to analyze in the anechoic chamber, which of course is precious, expensive time. So this was really a huge development, and it also meant we could help our customers, which now were in places like China or in Asia. And instead of hopping on a plane and going and doing the measurements on site, they could actually collect the data. We could help them remotely, not just set up the test, but we could actually hear what they were hearing. We could analyze what they were measuring. And that was huge.
I can
The
kind
other
of
thing,
see where this is going.
go ahead.
I just see where this is going, like be able to control the stimulus. And then now when you have kind of what I call it multipath, but like input and output coming simultaneously, I can guess where you're going to go next with this.
Yeah, it's really getting to the point where everything is being streamed through the cloud.
Mhm.
So if you can't, whether it's voice activation, multi-channel audio, it really requires that you can do this asynchronous type of measurements. And the neat thing too is once you got the recording, the calibrated recording, there's nothing to stop you from doing all kinds of interesting things with the data.
Mm. Okay, so it's all software based at this point, or do you also have your own hardware?
We do have our own hardware. It was funny in the beginning, I thought, Microsoft were geniuses because they were making a fortune off of software only, and they were, and it was smart. And then you start to see companies like Apple making hardware and basically the ability to combine really good hardware and software together. So there's all kinds of challenges, I'll say, just using a sound card. It can be tricky to set up, and it certainly can be tricky to calibrate. So we wanted to develop basically, you could even say our own sound cards in a way, but we wanted it to be more powerful in terms of being able to connect measurement microphones. You have to power the measurement microphone. Sometimes they needed polarization voltage. And also, we don't want to have all kinds of buttons and signal processing that could accidentally be changed that would mess up your calibration. And on top of that, speaking of calibration, every sound card, every audio interface is slightly different. There's some analog components into it. So you have to calibrate everyone individually. And to do that, you need a calibrated multimeter. You really need to know what you're doing. So even though we were supplying sound cards from third parties, we would calibrate each and every one of them and kind of give them a birth certificate, a calibration chart. But now if we stored that information on the EEPROM on our own audio interface, it would be plug and play. And on top of that, we could build in a power amplifier with an impedance circuit so that people could actually now just with one USB cable and basically hook a microphone and a loudspeaker to, for example, some loudspeaker cables. That was it. They could actually measure just about everything they needed to measure easily in one interface box, as opposed to having a sound card, a microphone power supply, an amplifier, an impedance circuit. And believe me, on the production line, that's huge.
Yeah.
If something goes wrong, swap and they're up and running.
Yeah, like the simplification of it, because depending on the production facility, there might be so many engineers that know how to set up that stuff, and then dozens of operators underneath them, and then anytime there's a delay in that guy coming to make sure everything's running properly, just backs up production. So that's interesting from a kind of our point of view being over here. So what have you been working on more recently? So what's going forward?
So as we all know, the audio products are becoming more and more sophisticated, complex. And we're basically trying to figure out how to test audio, which is just a subcomponent of maybe, video testing, all kinds of, component testing. So we have to make our test system plug and play into the big, production test system. So integrated with manufacturing overall. And this has required us to develop more tools like TCP/IP control that is basically software language agnostic. It also means that we had to create better ways to save data, more metadata, database connectivity, and even trying to make things more advanced in the sense that, what if someone wants to know what the humidity was when they made the measurement? How do we pass that information into SoundCheck? What if they want to barcode scan something like the serial number? How do we pass that into the measurement data? So that we've been developing all along as best as possible. And then on top of that, near and dear to my heart is perceptual measurements, because basically I want to know not just objectively how something measures, I want to know how it correlates to how we hear sound. And it's ultimately probably the driving force on a production line. If if it sounds good, you ship it. I don't care if it has, 20% distortion. If I can't hear it, I'm going to ship it.
All right. So yeah, these perceptual measurements, you told us this is what you wanted to kind of dig a little deeper on. So if the previous stuff had worked well, kind of maybe expand on that so that we understand what you're talking about with that.
Sure. So as I mentioned, the manufacturer, it's all about throughput and yield. And they only want to essentially detect audible faults if they're going to reject something. And then on top of that, we have a generation of engineers who really have only known automated measurements and frankly have not listened to speakers on a production line very much, especially now at the pandemic. I mean, there's very few R&D engineers go into production lines, they have their own engineers over there, or they basically rely on the manufacturer. So we also need to educate them how to relate measurements to audibility. And then last but not least, it's super important when you're setting up a production line to figure out what the limits should be. It's no easy challenge to say, hey, I want 3% distortion and that's it. If it doesn't correlate to audibility, what good is it? And then on top of that, all the conventional methods were basically very dependent on the product they were testing. They would have to make limits based on statistics that change versus frequency versus level. And at the end of the day, the human ear is pretty robust and pretty standard. If we can come up with a way to basically subtract out how the human ear perceives sound, we can come up with simpler, more reliable limits that tend to be, frankly, not so frequency dependent.
All right.
And I guess last but not least, I'll just say that, perceptual metrics done right are less likely to give us false results, even due to background noise. That's even another aspect of this.
Okay, so I think maybe you can run through some demo to kind of illustrate this for people a little better.
Sure, I'd love to.
I think
PowerPoint,
how
right?
are you digesting all this?
You've asked me?
Yeah, just asking you how you're digesting all this. You're the technical guy
Sitting
here.
back waiting for this juicy bit, perceptual algorithms. Here we go.
Good. Let me fire up PowerPoint here and share it with you.
Yeah, it's an interesting one because you do have this thing testing in a production line. So you might set up, a THD limit and a frequency response, upper and lower limits is a very standard thing. But how often is the product sounds wrong, but it still passes your test, or vice versa? Fails the test, but it sounds fine, And so
yeah,
it's a tough area.
I mean, if you're a product manufacturer and it fails, you say, well, what if we just open up the limits a little more,
Exactly.
more, and then everything passes and you're happy, but your customer is not necessarily happy, but until they find out. So, let me just start this slide here. I've been interested in distortion measurements pretty much ever since I worked at Apogee Acoustics. One of the interesting thing about ribbon loudspeakers was at high frequencies, I'll say mid-range frequencies, these ribbons had extremely low distortion. And at low frequencies, they had extremely high distortion. And it was just because of the magnetic structure. At low frequencies, it was very asymmetrical. And at the mid-range and tweeter, it was in a very big symmetrical magnetic gap. So I was always very interested in distortion audibility. And I could go on about, listening at what test level for distortion and so forth. But basically, both at Brüel and Care and then ultimately at Listen, I started getting really interested in what was audible for distortion. And rub and buzz was the one thing everyone could agree on. It just sounded horrible. Second and third harmonic distortion, that was kind of an interesting case where in some cases, even ordered distortion actually makes the sound more warm and can be good. So I just said, I was focused on production line testing, and I said, let's come up with a better metric for rub and buzz testing. So originally everyone was doing high order harmonic distortion. Then I was trying to get into more, I'll call it, ways to remove the frequency response impact on how we measure distortion. Then I was thinking, well, that's periodic distortion. What about transient distortion, which I'm happy to talk about as well. And then as always, it's like, well, what if you got music and what if you have speech? Can you, is that going to give you different distortion audibility? So over time, we started to develop these perceptual algorithms which took into account things like tonal masking and loudness, and how humans perceive loudness, not sound pressure level, but things like weightings. A weightings were really crude early loudness weighting filters. So we came up with what we call perceptual rub and buzz. And it was basically designed for end-of-line testing, but it could also be used for R&D to a certain degree. And we really wanted to refine it over time. And I will kind of give you a little story in a moment about why it became painfully obvious to me that we needed to improve it. But I'll talk a little bit about how the algorithm works, and then also a little bit about noise immunity, which is really why so many years later, from 2004 and just last year, we refined it. So basically, the traditional, what I'll call high order harmonic distortion, it does work well for catching defects, but there are some cases where you'll catch things that you can't hear. So this is a problem because, again, the manufacturer's like, hey, I can't hear that distortion. I can measure it, but I don't care. I just want to ship it. So next, you basically say, well, how are we going to come up with a distortion metric which hears like the human ear? I mean, that's been around for a long time. People have been trying to do that. But fortunately, there was some really good tools coming out that had to deal with, actually goes back to MP3 players and how they were trying to throw away signals that we couldn't hear. And we basically applied it to distortion. So in 2011, we came up with this metric for perceptual rub and buzz. And one of the first things we did was apply masking curves, which was pretty well understood, but frankly is also not black or white. The other thing is we wanted to take into account equal loudness contours, which is really a more sophisticated way of measuring perceived loudness, not just using A weighting, which is used and abused, or overused and abused. So we tried to move away from measuring distortion in dB or percent to measuring it in FLONs, which is a measurement of loudness. If I had more time, I could go into the specifics of the technical details, but bottom line is it correlates better to how humans hear sound, how the filters inside the human ear work, and that's also how we perceive level. But one of the really interesting things was, I think the next slide will talk a little bit. No, I'm sorry. One of our customers discovered that we are influenced how we hear distortion by background noise. In other words, if we're in a noisy environment, it's harder to hear distortion because it gets masked. So our original algorithm was hearing distortion just like a human ear. And if there was a lot of background noise, lo and behold, the perceptual rub and buzz would actually go down. And this clever customer on the production line said, you know what, I'm going to open up my test box and let more noise in, because then I'm going to pass more loudspeakers, because some of their customers were saying, you must use this. And I'm like, oh, very clever, but that's not the point. So basically, we needed to make a better refined perceptual rub and buzz algorithm that didn't take into account background noise, even though, quote, that's how the human ear works. Mm-hmm. So ultimately, we wanted to measure that loudspeaker on a noisy production line as if we were measuring it in a quiet room, which has always been, the quest of production testing, is how to eliminate the interfering background noise. So it was even more complex than that because of the masking curves. So we basically came up with a way to reduce the background noise while still applying the masking curves and the loudness algorithm. And at the same time, we didn't want to slow down the measurement. On the production line, speed is everything, throughput's everything. So we wanted to be able to do it simultaneously with all the other typical measurements, frequency response, polarity phase, you name it. So it took a bit of work, but we did come up with something that made it much easier to set limits. And of course, now the limits were more or less a flat line on a fawn scale, not on a percent distortion scale. And what we did was we focused on how to reduce the noise by, it's not just simple filtering, and I don't have time to go into a lot of detail because there is a lot of signal processing going on, which also in effect adds noise. But the other thing we worked on was masking curves are not black or white. And there are different masking curves for different types of signals, whether it's broadband signals or even sine waves, they're different. And what's even more confusing is a lot of the ones for sine waves were based on just what was called a masker and a maskee. So basically two sine waves and trying to determine whether the bigger sine wave level was masking out the smaller one. So we did a lot of research to figure out what was the best way to apply these masking curves and to take into account, even if we're measuring the loudspeaker in the near field, what is the perceived level in the far field where the listener is listening. And that is important because that determines also how much they can hear the distortion. So this is quickly just my desktop setup here. Kind of my playground, you could say. And I'll show you some measurements on these three loudspeakers. There's a good quote speaker, there's a rub and buzz speaker, and there's one in between. And as I mentioned before, sometimes using headphones to hear what the microphone is hearing is very important because it's not the same as holding a speaker up to your ear. It's certainly not the same as a speaker, like a micro speaker that's in some sort of ear coupler. So here are the three loudspeakers. Here's the good one, and hopefully you'll be able to hear this. If I hit play, can you hear that? Good. So that's just a pure tone at 256 hertz, which is roughly the resonant frequency of this loudspeaker. You can see what we call the perceptual rub and buzz versus frequency on fawn scale. So it's like under 10 fawns, which generally is what we call the threshold. And then you can see the spectrum at 256 hertz. And you can indeed see some second and third harmonics, but you see very little what we call higher order harmonics, like 10 through 50. Now let's go to the bad sounding loudspeaker, and hopefully this will be quite obvious. We can see there's quite a bit more distortion, harmonic distortion. Whoops, sorry. So hopefully that's quite obvious. You can really hear the buzzing sound. You can see the buzzing sound. What's interesting is I'm just playing 256 hertz here, but when you're doing a sine sweep, sometimes it's not just at resonance where you get maximum excursion. You can actually, this speaker, you can hear it through most of the sine sweep, even up to 1 kilohertz. But it's very evident here that we got high order harmonics. And if we look at the so-called borderline speaker, and this is one of the things I'm really a stickler about when you're setting limits, is measure a bunch of good speakers, measure a bunch of bad speakers, but also try to find some speakers that are just perceptually bad. Because if your limits should be able to hover very close to the borderline, and it's always good to, again, have that subjective-objective correlation. So here, you might not be able to tell over the quote internet here, but this one has a little bit of buzzing. Just to go back to the good speaker. Right. If you can hear it, sounds better, hopefully. But again, you can hear it, hopefully. You can see that the perceptual rub and buzz is just hovering over 10 fawns. So that's why, generally speaking, we can set a flat limit around 10 fawns. But it can...
Steve, the tones that you're playing are the recordings from the measurement microphone, is that right?
Yes, thank you for clarifying. That's actually the speaker, the ones that I was showing you earlier, playing back that tone. So if we move on here, and I'm sure I'm probably a bit long-winded, so I'll speed things up a little. The interesting thing here was the original algorithm was doing a pretty good job of catching these defects, but you could see in a noisy environment, we measured the same speaker 10 times, and because of the background noise, it gets a bit, fuzzy. And it makes it difficult to set limits, because if we look at a limit between the borderline and the bad speaker, you got to be very careful. But the new algorithm has a lot better noise rejection. And even though we measured this exact same 10 loudspeakers on the left, we now see that the variance is much smaller. And it's not perfect. I mean, background noise is always going to be difficult to isolate, especially because of the dynamic range. We can have, the human ear can actually hear 0.01% distortion in some cases of high order harmonics. So you really do have a huge dynamic range between the fundamental and the harmonics. And in a noisy factory, even with a good test box, you're not going to get it all out. Just reference some competitor has been trying to reproduce the same approach. You notice that they're a little bit behind, and that they still have the noise influence in the measurement. And I don't know why, but they also had a little bit of an issue at low frequencies, where the borderline, they claim, measured worse than the bad speaker, but that's not what we're hearing. In any case, if there's any questions, sorry, I could probably plumb ahead.
Could you go back to the slide with the good, bad borderline?
Sure.
And the enhanced perceptual RB is showing as a function of frequency. And you played us tones. Are you just playing us a tone to demonstrate the issue, but the measurement is actually, or this perceptual buzz and rub and buzz is generated from a chirp?
Yeah, thanks for pointing that out. So if you do like a very fast sine sweep, a chirp, it's actually pretty hard to hear the distortion. It just goes by so fast. But that's what I'm showing you on the left. These graphs are actually, I think, about a second and a half sine chirp, if you want to call it that. And in order for you to really hear the difference, it's just much easier to play a steady tone. So what I've done is the recordings are actually that I'm playing back are at 256 hertz, and the spectrum on the right-hand side is at 256 hertz. It turns out because that's where it's worse due to resonance and maximum displacement. But the algorithm is actually measuring versus all frequencies.
Yep. So that chirp signal is used also to calculate frequency response, phase, stuff like that. So that one signal is then used to generate this variety of results, including the...
Yeah, it's used for everything from frequency response, polarity, phase, distortion, and it's even applying some teal small parameters as well, looking at the, it's measuring impedance as well, and looking at some basic teal small parameters.
Yeah. And the enhanced perceptual rub and buzz is turning to a flat line at about, say, 2 kilohertz or something like that. Is that a factor of insufficient harmonics to work with?
So no, typically we suggest putting a flat line at 10 fawns from whatever over the entire frequency range, because we've removed the ears nonlinearities from the picture, because that one of the things that we often forget is that when we're listening to broadband signals, our ear is greatly influencing if you want to call it, the distortion because of its nonlinear frequency response. So we're effectively removing that and making it a flat line. There are some exceptions where you might, depending on your product, certainly a micro speaker and a smartphone, you're probably going to allow a certain amount of rub and buzz, audible rub and buzz, where if you're making a very expensive high-end loudspeaker, you probably don't want to. So there is some cases where you might want to adjust the level for the limit of the perceptual rub and buzz and fawns.
Yep, and this result in fawns, is that level independent? What I mean to say is that if you were to measure the speaker, not the speaker's distortion, but if you were to have a higher or lower input signal, does that shift up and down? Or is it more like a frequency response function where you're dividing out the input signal level?
Right, so that's a good question. So basically, what is independent is how we measure fawns is level independent. But speaker, of course, the louder you play it, typically the more distortion you get.
Yep.
So that's why you do have to. I always recommend on a production line they test at the highest level possible, because that's what their customers are going to do.
Yeah.
And it's a good way. You're breaking in the loudspeaker. You're really, it's better it fails on the production line than at the customer. And you can still measure everything you need to measure at a high level. I mean, obviously you don't want to break the loudspeaker, but you also get a better signal to noise ratio, and you'll be able to filter out background noise better.
And this, like the fawns level, is it something like a THD, although you mentioned doesn't quite work, but let's say if you were to set a limit 10% THD, you're going to hear it's going to be bad, there's your limit. Can you do the same thing with fawns and just say, all right, it doesn't matter what speaker I'm dealing with, I'm going to say 30, is my limit.
Exactly. You can pretty much use the same limit regardless of the speaker, whether it's rolling off at 100 hertz or 50 hertz. You can use the same limit, because you're effectively removing the fundamental frequency response's impact on the harmonics.
Yeah. And
it's kind of what we call normalized distortion, but that's a whole nother topic.
Okay, if you have something that is like a low pass filter effect, do you need to modify your bandwidth that you're going to test over? Because as you go down to no signal, it will appear as though the distortion goes to infinity, something like that?
No, but what will happen is you'll get more noise. And I actually have a slide in a minute which shows the impact of noise on the measurements.
Okay.
So let me go to that, because that's actually a good one. Let me go back here. So we wanted to do a thorough comparison of results with and without background noise. And one of the beauties of signal processing and also of SoundCheck was we could make a recording of a buzzing loudspeaker in a quiet room, and we could also make a recording of the background noise in a noisy factory. And then what we could do is analyze using our original PRB algorithm, which was more sensitive to noise, to our new ePRB algorithm, both with and without the factory noise. So it's hard to see, but this compound stimulus is actually the recording in the quiet room mixed with the factory noise. So, it's a real mix. I don't know how to call it. Yeah. But the old PRB algorithm, as I mentioned, when you added noise, the red curve is actually with the factory noise. So the measured PRB in fawns went down, just like a human ear would be masked the distortion would be masked by when the human is listening to it. So that was what this guy in the production line figured out by letting more noise in. But the new algorithm, it's certainly not perfect, but you can see, regardless of the factory noise, especially above 100 hertz, we get essentially the same result. At low frequencies, just as you mentioned, this speaker is actually, if we looked at the spectrum of the background noise and the frequency response, we'd actually see the background noise at 50 hertz is greater than the output from the speaker. So we have a negative signal to noise ratio, essentially, and we can't really do anything about that. So it is a little higher in the case where the background noise is literally got a negative signal to noise ratio. But it's a huge improvement. I mean, it's on the order of 10 to 20 dB, which is significant. So hopefully that helps answers some of that.
It does.
Great. All right. So sorry for the sales pitch, but I'll just run through this quickly. So basically, this was great because now people who were saying, hey, we don't get the same perceptual rub and buzz every time we measure because of the factory noise. We want to get better correlation, but we still want a fast throughput. And this really, I think, answers a lot of those complaints.
Mm-hmm.
And then, of course, the limits are easier to set because, again, the measurements are more repeatable. So
Okay.
I think that's pretty much it for PRB.
Okay. Yeah, maybe want to. I think you mentioned you might want to preview some other algorithms that you got coming, but maybe let's keep it to a limited preview. We could probably save some of that content for a future episode.
Yeah, and by the way, a lot of this is we have a YouTube channel and we have pretty extensive webinars on some of this stuff. So
Okay. Yeah, we'll put the link below for everybody to go check out. All right, that was quite a bit actually for one episode. So the perceptual algorithms render line tests for enhanced perceptual rub and buzz. Thanks, Steve, for that briefing on it. So we're going to end here for today. So please like, subscribe, share, hit the notification bell, all that good stuff. And we'll see you here in the next episode. Make this a two-parter. And Steve's going to get into enhanced loose particle detection. So a little crap that gets into your speaker. How do you detect that there's something in there, and how to detect it using his SoundCheck system. So come back next week to check that out.